Yesterday we looked at some polynomial theorems, today some results. So if we know a polynomial has k distinct zeros, now each one of those zeros could create a linear factor. So therefore, what we get when we multiply all those linear factors together must also be a factor of the polynomial. So in other words, x minus a, x minus a2, x minus a3 and so on, whatever that would be expanded out would also be a factor of the polynomial. So let's use this idea. We're going to show that 1 and negative 2 are zeros of this polynomial, and then go and factorise the whole thing. We sub in 1, yep, sure enough we get 0. Sub in negative 2, we get 0. So yes, x minus 1, x plus 2 is a factor. But how that helps me in the overall factorisation is that I can expand out the x minus 1, x plus 2. And I know that's going to be a factor. And now I can use logic to get the other factor. So leading term times leading term must give me leading term. So x squared times x squared. Constant times constant must give me the constant. So we have 5. So the question is, what is this missing term? It's going to be something x. So how many x's do I have at this stage? Well, I've got 5x already. So it looks like that's as good as it's going to get. But I might double check just to make sure. What about the cubes? How many cubes would I have at the moment? Yeah, no, that confirms it. We get x cubed as well. And if you're still unsure, let's have a look at the squares. What do we got at the moment? I'd have 5x squared minus 2x squared, which is 3x squared. So yes, that is it, completely factorised. But now I'll put that x squared plus x minus 2 back into its linear factors. And then we also have x squared plus 5 as the other factor as well. So the next idea. Again, if the polynomial has n distinct real zeros. So that's a little bit different to the first one. The first one was just saying it's a factor. The second one is saying, no, this is all of them. They're the only factors. Well, if that's the case, then that's the polynomial. X minus a1, x minus a2, and so on and so on. Well, if it's monic, of course, if it's not monic, there might be some constant number out the front as well. What it's saying is a polynomial of degree n cannot have more than n zeros. It's not possible. Because if it did, it would then have another factor, and then that would make the leading term higher than x to the power of n. Not possible. So any polynomial of degree n cannot have more than n distinct zeros, which is actually different to the number of roots, by the way. A polynomial will always have the same number of roots as its order. So a quadratic will always have 2 roots. A cubic will always have 3 roots. Now, some of those roots might be the same, some might not be real, some might be imaginary, but they'll always have the same number. But when we talk about zeros, we say, well, I can't have more than n zeros. Could have less, but not more. We're told a polynomial has a double zero at negative 7, a single zero at 2, write down a possible polynomial, and by that they mean one that will generalise it for every possible polynomial. So I know these two things are factors, that's certainly true, but what else could we have? Well, it could be times another polynomial, but that other polynomial can't have a 0 at 2 or negative 7. Because if it had one, say, at 2, then my polynomial would no longer have a single 0 at 2. It would have a double one. And similar with negative 7. If it had one at negative 7, it would no longer have a double one, and now be a triple one. But any other polynomial could go there and it would satisfy what they're saying here, because it didn't mention anything about the degree of the polynomial. I could have more factors there. The other thing, do I need to put this or not? I just did, because I'm saying, well, it could be any multiple of it. That could be inside the QX itself, of course, so maybe you don't need the K. But what about if it said, oh no, it's got to be a monic polynomial of degree 3. I'll write down the 2 pieces of information that they told me, and that's it. There's nothing else it could be, because they've told me it's of degree 3. Well, that's of degree 3. So I can't multiply it by another polynomial. And they've also told me it's monic. So I can't multiply it by a number. There's only one possibility for this one. If they said a monic of degree 4, again, I know these are factors, but if I want to get it to degree 4, at the moment it's degree 3, I must multiply it by a linear factor. So I'll multiply it by x minus a, but a can't be 2 or negative 7 for the reasons that I mentioned before. It would change the order of that 0. The double would become a triple and so on. Polynomial of degree 5 then. At the moment I've got a degree 3. I would have to multiply by a quadratic. So it's a polynomial of degree 2, but again, can't have a 0 at 2 or negative 7, or it'll change the nature of those zeros. And yeah, I could multiply it by a constant number because they didn't say it was monic. So I could have that there. This is where it looks like I'm contradicting what I said. Because number 3 said you can't have a polynomial with more than n zeros. And now I'm saying, well, if it does, then it must be this really weird polynomial that we call the zero polynomial. And the zero polynomial is just 0. I mean, 0 is a polynomial. What is the solution to it? Well, everything's a solution to it. Because if it's the constant number 0, we're saying no matter what we substitute in, we're going to get the answer 0. So how many zeros does it have? Well, it has an infinite number, because you can put anything in there and get the answer 0. But what's the degree of the zero polynomial? Well, that's an interesting question in itself, because you don't have any x terms, and we said the degree of the polynomial is the highest power, but it's nothing, it's 0, there's nothing there. This is the problem with 0 as a number. It's weird. You can't divide by it, you can't have 0 to the power of 0. All these problems happen with 0, and it's the same with polynomials. So there's this special polynomial we call the zero polynomial, and yeah, theoretically it does have more than n zeros. If you know two polynomials, and notice I've got the congruent symbol there, not the equal symbol. So if we know they're congruent, so they're identically equal. See, if it was just an equal symbol, we'd be saying, solve this equation. For what values of x are these equal? When we put the congruent there, we're saying, no, it doesn't matter what we substitute in for x, they will always be equal. So they are identical. So that means all of the coefficients of every term must be the same. So what do I mean by that? If the polynomial on the left is congruent to the polynomial on the right, then I can say, well, look, all these coefficients must be the same. So A1 must equal A2, B1 must equal B2, C1 must equal C2, and so on, all the way down for all the different coefficients. So we get a question like that, we can set up a whole heap of different equations to find the different values. All right, that shall do us for today. 10E.